Hello, this video is entitled Parametric Equations and Calculus. Alright, let's see. The first theorem we're going to look at is parametric form of the derivative. If you have a smooth curve C, and essentially smooth curve means that you don't have any sharp points and you don't have any gaps or discontinuities in there. So x equals f of t, y equals g of t, then the slope of the curve C at the point xy, which is just dy dx, but dy dx can be solved by finding dy dt divided by dx dt. Of course, provided by that dx dt would not be 0. So this isn't too bad. So here's a parametric equation where x equals square root of t, y equals 3t minus 1. We're interested in finding the slope at t equals 1, which you could easily figure out at what point that is in rectangular coordinates by putting 1 in there. Or if you don't want to, you don't have to, but you put 1 in there, square root of 1 is 1, 3 minus 1 is 2. So in rectangular form, it would be at the point 1, 2, which I have drawn on the graph over there. Which the graph isn't necessary, but there it is at 1, 2. So I took dx dt first, even though it'll be in the denominator. So t to the 1/2 would be 1/2 t to the minus 1/2. Then dy dt would just be 3. So dy dx will be dy dt on the numerator, which is 3. And then there's no t to plug 1 in there for. So here you put 1 in there. So it's 1/2 times 1 to the negative 1/2, so which is just 1. So 3 divided by 1/2 is 6. And 6 looks like a reasonable slope for that line. Like I said, we don't have to graph it and check, but now that it was there, I just wanted to show that it looked reasonable. All right, that's basically the gist of how you do that. Let's see. Now suppose on a parametric equations, smooth curve, we wanted to figure out what's called both vertical tangencies and horizontal tangencies. So remember, these don't have to, we're not graphing them, but they don't have to be functions of x. In other words, they can be parametric forms that form, ellipses or circles or whatever. So we're not, if we were just y as a function of x, there could not be vertical tangents. That would be where the derivative is undefined. We would only be looking at horizontal tangents. But here we can look at both. So to find vertical tangents, we're looking for anywhere values of t where dx dt equals 0, and a horizontal tangent will occur at values of t where dy dt equals 0. So let's give this a whirl and see what happens. And also, okay, I'm going to throw in, we're going to find the equation of the tangent line at t equals 2. So that means we will need to find the derivative. That we just learned how to do. So here's our parametric set of equations. X equals t squared minus t plus 2. Y equals t cubed plus minus 3t. So dy dt, this derivative would be 3t squared minus 3. The derivative of x would be 2t minus 1. So if I put t equals 2 into both of those, I get 9 for this one, 3 for this one. Therefore, dy dx would be 9 divided by 3 equals 3. I didn't specify, but yeah, you would have to be done in rectangular form. You couldn't really do it, the equation of the tangent line in rectangular form. So all I have to do now is take y equals mx plus b. I know the slope is now 3. So what I have to do is find out what x and what y is based on t equals 2. No problem. Just plug them right back up in these two equations, which I've done on the next line down here. So you see that x of 2 will equal 4. Y of 2 equals 2. So when t equals 2, you're at the point 4, 2 on the graph. And so there's my x. There's my y. I can now solve for b. Put in 2 for y, 4 for x. 3 times 4 plus b. b equals negative 10. So y would equal 3x minus 10. Now to find the, doesn't matter which one you do first, vertical or horizontal tangents. The vertical tangents are done as solving dx dt equals 0. So dx dt was 2t minus 1. And we're actually finding the rectangular coordinates. So t equals 1/2. So I then need to know what x and y is when t equals 1/2. So, obviously use your calculator for this mess right here, but just plug in 1/2 for x and y, come up with that coordinate. So it's going to be at 7/4, comma, negative 11/8. 11 over 8. And dy dt, so the derivative was 3t squared minus 3. Set that equal to 0, it gives you 3t squared equals 3. T squared equals 1. Gives you plus n minus 1. Don't forget that. So there's two values here. So we have two t's, which will then generate two separate coordinates. So if you put negative 1 in there, it's going to be at the point 4, comma 2. And you put positive 1 in there, it's going to be at the point 2, comma negative 2. So this is, not mandatory, but I just wanted to give you a visual look of what happened here. So I put, now what I did is, the first set is obviously the original equation, your parametric equations. Now this next pair is I parameterized the line y equals 3x minus 10. So what I did is said, okay, y equals 3x minus 10 converted to parametric is I just said, okay, let x equals t, and then y would just be 3t minus 10. So you can see that was the second pair of equations, t, 3t minus 1, because I wanted to actually graph it instead of me hand drawing it. So the blue represents that, little fishy looking graph or whatever that is. Looks like a little fish or something. And then you see the red line there is graphing at the point 4, 2. I'm sorry, not point 4, 2. What was that point? Excuse me. That's the horizontal tangent. I guess it was 4, 2. Yeah, so it is right here, which also just happens to coincidentally be a horizontal tangent. That was just coincidence. But anyway, that red line is tangent at that point. That's because the graph's crossing over itself there, so that's why that could happen. But yeah, that's the tangent line at 4, 2, and that's also one of the two horizontal tangents that we just found. So there's the two horizontal tangents, and then the purple line represents that vertical tangent. That was the one that had the weird fraction, 7/4, negative 11/8 right there. And then there are the two horizontals. So, and there I was sort of explaining or writing out what I just explained about how to create these two. So, very good. All right, here's one with the trig function. Yeah, it's got a little too many of them in there, but that's all right. It's good trig practice. Well, never hurts us to keep our trig skills sharp here. So here's the parametric x equals cos of theta, y is 2 sine of 2 theta. And I'm restricting this between 0 and 2 pi, inclusive of 0, not 2 pi. I don't want to have both 0 and 2 pi as an answer. Because, you've already covered the entire graph by then anyway. So let's look at the derivatives. The derivative of x respect to theta will be negative sine of theta. We set that equal to 0. Theta will be 0 and pi. So to figure out what those are in rectangular form, we plug them into these two. So 0 would make it 1, and then 0 would make this 0. So you have 1, 0. And then when you put pi in here for cosine of pi is negative 1, and then 2 sine of 2 pi would still be 0. So those are your 2 points with your vertical tangents right there in red. So that graph looks kind of like a little bow tie there, doesn't it? So there are the two vertical tangents. Looks like there's 4 horizontals. And so here's my derivative. Actually, so don't forget the chain rule, of course. So the derivative of 2 sine of 2 theta, you have to take the derivative of 2 theta, which will be 2, so it makes it 4 cosine of 2 theta. Now, this is just the way I like to do this. You might do it differently, but you have to be careful with these, multiple angles here when you're solving trig equations. So, okay, the 4 won't matter because we're looking for cosine of 2 theta equals 0. And so what I'm going to do then is just use an arbitrary variable u here. We could have used anything we want here. So I'm looking for cosine of u equals 0. Now I went beyond the 2 pi, but you'll see why I did that here in a minute. So I just kind of, cosine is 0 at every multiple of pi over 2. So I went 1 pi over 2, 3, 5, 7 pi over 2. Now I could have kept going, but I did not need to go beyond that. I'll show you why here in a second. Well, if we know that cosine of 2 theta equals 0 and cosine of u equals 0, that means u will equal 2 theta. So therefore, theta equals 1/2 of u. So you just take half of each of those angles. So then the reason why I didn't need to go 9 pi over 2, half of 9 pi over 2 is 9 pi over 4, and that would be beyond 2 pi. So that's what I mean. But obviously, you could have listed these out and then realized you were beyond 2 pi. It's not critical that you had to stop it at the right place. You could have corrected that. So there are 4 values: pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. You plug those into the original equations for x and y, and I'm not going to do all that, but here they are. Here are the 4 points, and that's the 4 blue horizontal tangents on that graph. All right, that's good trig practice. I like that. Now, let's find arc length in parametric form. Okay. Now, this might sound familiar because, wait a minute, didn't we already do arc length in this class? Yes, we did. We did it in rectangular form. Now we're going to do it in parametric form. The rectangular form was 1 plus the derivative f prime of x squared from a to b. Here, it's f prime of t squared plus g prime of t squared, the square root of all that, dt. So I just kind of drew a little picture here. So we're trying to find what that length would be if you straighten that line all the way out. So obviously, you can use the definite integral capabilities of your calculator to figure this out, but unless on a handwritten test I'm requiring exact answers, and you might have to work it out, but because if it produces some sort of radical answer, but basically you should be able to use it. But anyway, I have to though pick problems though. I want to make sure that they can be integrated by hand. In other words, I'm not going to pick something that cannot be worked out by hand. So let's look at this one. X equals 6t squared, y equals 2t cubed, t from 1 to 4. It's not exactly a very exciting looking arc there because it almost looks pretty straight, doesn't it? That's all right. It can be integrated, so that's the main thing. So the derivative of x will be 12t, the derivative of y will be 6t squared. So we have the integral from 1 to 4, the square root of 12t squared plus 6t squared squared, which gives me 144t squared plus 36t to the 4th, all under the radical. Now you can't break up a radical by addition and subtraction, only multiplication and division, but you can factor out a radical. So if there's a common term like this a here, but it factors out then as the square root of a and still leaves b plus c here. So it's very important you realize the square root of a plus b is not the square root of a plus the square root of b. So there's a 36t squared that would go into both these two terms. So I factor out a square root of that. So it has square root of 36t squared plus times the square root of 4 plus t squared. And the square root of 36t squared, technically, by definition, it's really 6 absolute value of t. Because technically the square root of t squared is really the absolute value of t. But since that would only make a difference if these were negative numbers. But since they are positive, we just use t. So I pulled the 6 out. And then here we go. Now we got it. So it boils down to a u substitution problem. This one does kind of have a weird looking answer. You know, like I said, on a handwritten test, I would want you to come up with this exact answer. So don't totally rely on the calculator. Obviously, integration is an important skill to know anyway. U equals 4 plus t squared. Du equals 2t dt. So 1/2 du equals t dt. Change the limits. So you put in 4, you get 20. Put in 1, you get 5. And I never have to go back to x again. So I pulled the 1/2 from the du out with a 6. So that's going to make a 3. The antiderivative of u to the 1/2 would be 2/3 u to the 3/2. So the 3's will cancel, obviously, and leave a 2. So I just have a u to the 3/2. Put in 20, put in 5. So what I have flagged here is a correct answer. 20, but you could also see it written as 20 times the square root of 20, and then 5 times the square root of 5. But I put this problem in Maple just to show what it gave. Now, when I say exact answer, to me, this I consider correct. What I'm doing right here is not really that important. I just wanted to show how that Maple answer came about, but I would not expect a student to necessarily have to do that. In other words, if I said I want an exact answer, that's an exact. Exact means not decimal. Well, not like infinite decimal. I mean, technically 2.5 would be an exact answer if it was 5/2. But this would be perfect here. You would not have to do all of this business right there. Well, you could look it over and see if it looks fascinating to you there or not. It's not that bad, but let's try another one. X equals arc sine, y equals natural log of the square root of 1 minus t squared, which by log properties, I can bring that power of 1/2 down to the bottom, which I like to do. Anytime I can use that log property, I always do that. And we're going from 0 to 1/2. So the derivative of arc sine of t would be 1 over the square root of 1 minus t squared. That 1/2 makes this easier. The derivative of natural log is the derivative of what's in the parentheses over what's in the parentheses. So it'll be negative 2t's, that derivative, over 1 minus t squared. The 2's reduce, so it's negative t over 1 minus t squared. So now, this looks like it's going to be ugly, but it's actually going to clean up pretty well here after a couple of algebra steps. So you take the first one here squared, now we take the second one squared. So the squaring, this one gets rid of the square root, so I have 1 over 1 minus t squared plus t squared over 1 minus t squared squared. So I want to get a common denominator between these two. So the one on the left is just missing another 1 minus t squared to make it match that one. So that's what I'm doing over here is I'm taking it and multiplying both top and bottom by 1 minus t squared. And that gives me this, 1 minus t squared over 1 minus t squared squared. So that's what I now have replaced right here. And then by doing that, I now have a common denominator. Then just look what happens by coincidence here. And that's a very important coincidence, but the t squareds here cancel. So I come down here, and then the square root of 1 minus t squared squared is just 1 over 1 minus t squared. Now, you wouldn't necessarily have to have this formula. You know, if you needed it, I'd probably provide it. But, you know, this problem could also be integrated by partial fractions. You can break that down and do that manually then, so it wouldn't be that bad. It'd be a 1 minus t and then a 1 plus t, and you could work it out. So this is just a condensed version of the partial fractions answer. But I wouldn't necessarily expect you to have this formula on your list of formulas for this particular. Although since this is on the final exam, this section is, but you probably would have that formula down there somewhere. So anyway, so now we just plug this into everything. The formula is pretty straightforward from there. So I put in 1/2, put in 0. I'll get natural 1/2 on the outside, of course. 1/2, 1 plus 1/2 is 3/2. 1 minus 1/2 is 1/2. And then 3/2 divided by 1/2 is 3. Here I get 1 and 1, which is 1. Natural log of 1 is 0. So I just have 1/2 natural log of 3. I just put the decimal answer there, but not usually wouldn't require that unless in a multiple choice question, maybe it would have the decimal, but it might just have these answers: 1/2 natural log of 3. There's the graph of the original function, so it's supposed to have a length of about 0.55, which I did the f and n, the old f and n function in the calculator without the integral sign. All right, very good. Let's see. Like I said, I don't want these integrals to be too excruciatingly complicated. Now this one's not too bad because it's just another basic substitution. Not too scary. X equals 3t, y equals 4t to the 3/2. So the derivative of x with respect to t would be 3. dy dt would be 6t to the 1/2, 0 to 2. And so I plug it in here, I get 3 squared. I get 6t to the 1/2 squared. That's going to give me 9 plus 36, all under the square root. So that's just a perfect u substitution problem. So u will be 9 plus 36t. du equals 36t. So I'd bring a 1 over 36 out to the outside. And then I'll change my limits of integration. I put in 2. 9 plus 36 times 2 is 81. And then put in 0. 9 plus 0 is 9. So now I have 1 over 36 from 1 to 9, 9 to 81, and u to the 1/2 du, and I never have to go back to x again. So then I have the antiderivative of u to the 1/2, which is 2/3 u to the 3/2, and then the 2 over the 36 here will make that 18. 18 times 3 is 54. So I have 1 over 54 of 81 to the 3/2 minus 9 to the 3/2. Now this happens to work out because 81 and 9 both have, whole number square roots. This works out to where the radical goes away. And actually it works out even to be an integer. But at a worst case scenario, we would have just gotten a fraction here, which would have been fine. But no radical is going to be here. So 81 to the 3/2 is essentially the square root of 81 cubed, which is 729. The square root of 9 cubed is 27. And it just happens to be 729 minus 27 is 702. Divided by 54 happens to equal 13. So that one is exactly arc length of 13. And there's a graph of it. All right. One more example. So we've got a circle here. X equals 5 cosine of t. X equals 5 sine of t. Which I just realized now, knowing this is a circle, you don't have to even do the calculus on it. But let me go ahead and finish it anyway. Because being a circle, the circumference of a circle is 2 times, or pi times the diameter, or 2 pi radius. Okay. Anyway. Well, okay, it's not a full circle, it's just a quarter of a circle, but I guess, you could use the circle formula and divide it by the circumference and just divide it by 4. But anyway, let's just pretend for a minute. I'll mention that at the end. But yeah, this really wouldn't be the best kind of problem. But it has an interesting feature to it that I like. So the derivative 5 cos is negative 5 sine of t. The derivative 5 sine of t, 5 cos of t. And then you square both of those, and you have 25 sine squared t plus 25 cos squared t. And this problem is like, you got to know that sine squared plus cosine squared equals 1, or there's no other mathematical way to recover from it. There's no other way to do it. So it's either like super easy once you see that, and otherwise it's impossible if you don't. But I factored out a square root of 25, but if you just recognize that was going to be 25, that's fine, because this will be 1 right here, so it just leaves the square root of 25 there, which will be 5. So you're really just integrating square root of 25, which is be 5t from 0 to pi over 2, which is 5 pi over 2. So the original problem is a circle of radius 5, and that means the circumference would be 5 times 2 pi, which is 10 pi. And if you divide that by 4, 10 pi over 4 does equal 5 pi over 2. But it worked out using calculus also. So, well, that concludes this video on parametric equations and calculus.